All right, everybody, thanks to I think this is the first UTIG seminar of the fall. And thank you all for coming. I am very pleased to introduce Louise Farquharson. She is from the University of Alaska. She also holds a position as research fellow at the University of Wrocław. I hope I pronounced that right. And is an honorary researcher at the University of Bristol. She works on Arctic geoscience and combines in situ monitoring, remote sensing, quaternary dating methods, and sedimentology to understand past and modern day response of Arctic landscapes. She's involved in a stunning array of projects with collaborators literally all over the globe, supported by DoD and DOE and NSF and Alaska. We were fortunate enough to meet and have the opportunity to work with Louise in Fairbanks studying permafrost. She introduced my group to the joys of coring in winter in Fairbanks. I can report it's challenging, and I've sort of flipped that opportunity for her by bringing her here, and she finds it very hot outside and very cold inside in her hotel. She received her undergraduate degree from University of Sussex and her master's and doctoral degree at the University of Alaska, working broadly in Arctic landscape dynamics. Her talk today is entitled Not So Permanent Permafrost. Let me just note that Kuwa will be leading the lunch. We'll meet at 11:45 in the, what do you call that, by the elevator. And the other thing is from 5 to 6, Louise is going to be at Austin Beer Works. So with that, I introduce Louise.
Thanks for that epic introduction, Peter. Yeah, it is really nice to be somewhere where the ground isn't freezing up in September. But I did pack incorrectly and check the weather forecast rather than thinking about what it was going to be like inside. So I bought one pair of trousers, and they're not very clean at this point, but hopefully you guys can't tell because it's been just the coldest trip I've been on ever, other than like Arctic research. Yeah, so today I'm going to talk about permafrost landscape dynamics and how permafrost landscapes are currently changing. And I wanted to just start talking about the indigenous peoples who have been on the landscapes that we work on for thousands of years. So primarily we work on Nupiaq and Athabascan lands, which you can see here in the blues and purple. And then I'm just going to kind of give you a brief overview of the talk, so there are no surprises. So I'm going to go through, I'm not sure how many people are familiar with permafrost systems, so I'm just going to go through some key terms. And then I'm going to briefly go over why would you care about permafrost here in Austin or just generally. And then we're going to kind of look at 2 case studies that our group's been working on in recent years. So we're going to look at some very cold permafrost up in the Canadian archipelago. And then we'll travel further south to interior Alaska to the discontinuous permafrost zone, where permafrost is warm, which is a relative term, but it's still below freezing. And then I'll touch quickly on implications for infrastructure and ongoing research before closing out. So, as we all know, atmospheric warming is taking place globally, but this is felt much more acutely at high latitudes due to Arctic amplification. And so we have quite a wide array of boreholes between our lab group and others in European lab groups and in Canada, where we can kind of check the health of permafrost through these long-term monitoring systems. And so you can see that in this plot, you've got time on the x-axis and ground temperature on the y-axis. And I've put this dotted line with a melting ice cream at 0 degrees Celsius to kind of show how some of these temperatures are creeping up towards this kind of pretty important threshold here. And so permafrost is warming at a global scale, and this is being observed across different landscape types. So in this talk, the overarching question is, how are periglacial landscapes responding to ongoing warming? And spoiler alert, they're not doing particularly well, and they're not very happy, and they're very melty, but we'll go into the details of it. So firstly, some key terms. What is permafrost? So permafrost is just ground that remains at or below 0 degrees Celsius for 2 years or longer. And we're going to expect that permafrost to warm with atmospheric warming and eventually thaw. So in this map, you can see different shades of blue. And essentially, the darker the blue, the more continuous the distribution of permafrost. So in the northern regions, permafrost underlies the entire landscape. And as we move progressively further south, it underlies less and less of the landscape until it's just present in little patches. So one thing that's really important to keep in mind is that permafrost does not have to have ice in it. Permafrost is just ground that is below 0 degrees Celsius, right? So we can have bedrock that is permafrost. We can have peat that's permafrost affected. But most interesting to me and a lot of other researchers is permafrost that does contain really large volumes of ice, preferably with lots of labile organic carbon in it that is going to be released as methane. So it's an exciting site. The next key term I want to introduce, and some of you may be familiar with this, is the active layer. So this is a layer that is subject to annual thaw and then refreeze, and it sits right on top of the permafrost. So during summer months, we get this thaw propagating down, and then during the winter, it refreezes from the top down. And we expect this to deepen with warming. The next term is ground ice. So massive ground ice is present in some areas of permafrost. And the distribution of ground ice and the characteristics of ground ice are really dependent on the...
Support, because if you do, you can just
I can do that.
do that as you wish.
Thank you. I should. I may not forget. You can remind me. Yeah, so ground ice distribution is very variable depending on quaternary geology, essentially, and past the depositional events. And it can be present in lots of different forms. I'll do this. I'll do this one. No, it's okay. Well, you guys can see the pictures. So anyway, the picture in the top left there shows it's called a massive syngenetic ice wedge. In the literature, you see them as kind of triangles in the ground when they're oversimplified, but they're really kind of amorphous kind of features a lot of the time. But they can be huge. They can be up to 50 meters deep and 30 meters wide. They're absolutely huge. So as they're melting and the permafrost around it is thawing, this can cause really significant changes to the surface topography. And you can see down here at the bottom, there's like someone kind of proudly holding up their permafrost core with a nice layer of ice in it too. So ground ice can be present as these ice wedges. It can be present as buried glacial ice, so relic glacial ice that's been covered up and thermally protected. It can be also in the sediment as lenses or interstitial pore ice. And so the presence of this ice within the landscape makes these landscapes really vulnerable to warming. And so the last picture here on the bottom right shows this kind of polygonal terrain that forms. So these ice wedges, they form from contraction cracking, and they create this quite pretty pattern. So when you fly over Arctic landscapes, you see just hundreds of miles of these ice wedge polygons in the tundra. So I've noticed that within our research, generally permafrost sampling is something that is really, really hard, but when it works, people are incredibly happy. So you can see here some very happy permafrost scientists who have retrieved samples from below ground. But because this is so challenging, we actually have a very limited idea of how the structure of permafrost, how much ground ice there is, where it is, and how much carbon there is. And so if we look at where material's been sampled from the permafrost, it's really highly concentrated in specific areas like UTIG in Northern Alaska, or Tule Field Station, or Abisko in Sweden. And then there's a lot of regions, most of Siberia, where we really don't have an idea of what's in the subsurface. And even more frustrating is it's actually really hard to get below about 1.5 meters. And so there's a lot that we really don't know about what's below the surface. So understanding future change is quite limited by where we've been able to sample for permafrost cores. So second to last term is talic. We'll go into this, but it's a layer of unfrozen ground in a region of permafrost. And so to date, the literature on talics is primarily focused on lake systems, where we have like deep lakes that facilitate the formation of a thaw bowl beneath the lake. But we're beginning to see subaerial talic formation propagating across the discontinuous permafrost zone in recent years. And then lastly, as I said, when this ground ice melts that I mentioned previously, we get this hummocky terrain called thermoclasts that form. So we have the ice was there, then it melts, and that change in volume results in the ground surface becoming hummocky, and you get water ponding at the surface in a lot of locations. So just quickly, also, why do we care about permafrost? One of the reasons we need to care about permafrost is there's a lot of critical infrastructure, a lot of communities located in areas of permafrost. So there's a extensive infrastructure associated with the oil industry, especially up in Alaska, in areas of Siberia too. But also about 5 million people live on permafrost, much of which is ice rich. So by 2050, projections suggest that up to 30% of Panarctic infrastructure is going to be affected by permafrost degradation. Here's a map of the communities across the Panarctic that are located on permafrost. Another more recently flagged issue is the issue of contaminant mobilization with permafrost degradation too. So this is a paper by Moritz Langer from 2023, where he mapped known locations of contamination in permafrost soils. So in a lot of areas, the military has treated areas with permafrost, ice-rich permafrost, as kind of a bathtub, right? It's like an aquitard where they think this is a frozen material, the contaminants aren't going to be able to go anywhere. So this is a great spot to just dump a load of contaminant material. And so now with warming, with talc development, we're getting much better hydrological connectivity. We're getting incomplete freeze in the wintertime. And there's going to be a really, really big issue with contaminant mobilization across these Arctic landscapes. And last but not least, probably what people are most familiar with when we think about permafrost is the methane time bomb, the carbon cycling, the big figures that are put out about how much carbon is stored within permafrost soils. And this figure, 1,500 petagrams of carbon, should be taken with a very large grain of salt. Like as I was saying, we don't really know how much carbon is beneath the surface. It's based on very limited sampling compared to temperate and tropical regions, but it does hold a significant amount of carbon. And so during these Pleistocene depositional periods, we had lots of carbon in the form of mammoth poop, mammoth bits, and planty debris being frozen in this giant kind of like sediment freezer that was until recently really happy and stable, but it now is thawing out. On the left-hand side here, you can see a popular pastime in Fairbanks, which is to take your ice pick, go out to the lake and poke a hole in some of the methane bubbles on lakes and then set it on fire. So yeah, just watch your eyebrows. I have been singed, but it is fun. So yeah. So one of the main issues right now with understanding how Arctic landscapes are responding to warming is that we are very skewed towards remote sensing based observation. It's really hard to get to Arctic sites. It's really expensive to get to Arctic sites. And yeah, it takes a long time to get out to these remote wilderness locations. And so it is really, these remote sensing studies hold a lot of worth, but they don't really allow us to understand what's happening in the subsurface a lot of the time. And so unless we can use remote sensing to study areas where we have long-term monitoring, it's hard to kind of couple cause and effect with the landscape responses that we're seeing in these permafrost landscapes. So our lab group primarily works on monitoring, or kind of bread and butter is like monitoring permafrost across the Panarctic. Up until recently, until NSF, after 20 years, stopped funding our monitoring network. But hopefully we can find some alternative funding for that. But so we have this pretty extensive monitoring network across the Arctic. The Russian stations, obviously for the last few years, have kind of been out on their own. Hopefully they're doing okay. But we have stations in Scandinavia too, and primarily Alaska, and then the Canadian Arctic too. And so what these sites do is enable us to kind of like keep an eye on permafrost stability, permafrost health, and look at how permafrost systems are responding to ongoing warming. So while we have relatively few direct observations, where we do have the ground monitoring stations, we can then couple like the warming or the different changes in ground thermal dynamics with above ground changes, and that enables us to tie together cause and effect more effectively. So I'm going to start by looking at an area up in the Canadian archipelago where we have 3 long-term monitoring sites that were established in the early 2000s. And this work was done in collaboration with folks from Alfred Wegener Institute and the Northwest Territories Geological Survey, as well as others at UAF. And so to get to these sites is quite the adventure. We had to drive all the way over to Dawson City, then up the Dempster Highway in Canada to Inuvik, where we got in a DC-3, and then we flew to our 3 monitoring sites. And it's funny because this is a field campaign with a crew of geophysicists, and they were just like, they spend 1 hour at the site, get the data, and we take the survey, and we go. And I'm just like, but we've got to like understand the geomorphological processes. So it was slightly painful, but I also got to catch these like snapshots of this really cool landscape, and we got to see some really cool changes as well. But yeah, so it was a 7-day trip, and we did all of that. It was pretty exciting. So it was pretty cool though. These guys, I actually see that someone here has flown with them, because this picture on the side shows some UTIG folks who are also in probably maybe even the same plane. It's a Kemboric plane. They fly between Antarctica and the Canadian archipelago. Basically, they alternate. They just spend the whole time in winter, which is kind of wild. But anyway, it was a great adventure to get up there. And so these sites are characterized by very cold. This is kind of some of the coldest permafrost we get on the planet currently. So we have mean annual ground temperatures at a meter depth is about -15 degrees Celsius. So it should be really, generally the literature considers these sites to be really stable. Projections of where permafrost degradation is going to take place. Generally, these sites are all blue. It's really good. Out to 2100, everything's really stable. To give some context, I realize that we're in Texas, and the term cold, it's -15, like very cold versus cold. So permafrost in Fairbanks is like -0.5 degrees Celsius at 1 meter depth at mean annual ground temperature. So that stuff is like on its way out pretty soon. And this permafrost further north in the Canadian archipelago is a lot more colder and was considered a lot more stable. So at each of these sites, these 3 sites, we've got Banks Island, Mold Bay, and Isaacson, have been monitored since 2004. This is one of our monitoring stations. They're pretty basic. We just have thermistors in the ground. At some sites, we study a lot more variables, but because these sites are kind of left alone for years at a time, we basically get to go up there, have to do some basic maintenance, and then just like hope, that they're going to keep running. And we have modems attached to them so they can transmit data to us so we can kind of check on them. But sometimes they'll just go down for like a few months and then come back to life. And it's a very emotional experience working with these stations. But so we now have like about 2 decades of ground temperature data for these sites, which is pretty awesome actually. But when I got there, so I'd worked only in areas in warm permafrost or in the North Slope of Alaska. And so these landscapes are, they're lush, they're like tropical compared to these sites. And so we have these like thick peats, like really, really moist, thick peats, these sphagnums that grow. This is kind of around Fairbanks. You see this top right picture. And we got out of the plane at, this is Mold Bay, lovely name. And there's no vegetation. There's no organic mat. There's no protected peat layer. It's just this cryptogrammic crust and poppies. Tons of these like really pretty poppies everywhere, basically the only plant that was growing. And what's really interesting about this is that this is a landscape that is really susceptible to fluctuations in air temperature, because the heat can flux into the soil very, very quickly. Whereas when you have a peat protecting the underlying permafrost, it's kind of a buffer that like attenuates the flux of heat into the ground. So we have this very important characteristic of the site that makes it actually a bit more vulnerable than we realized. And the other thing that we looked at these sites, this is from 2004. I wasn't on this trip when they first installed the monitoring equipment, but during this campaign, they dug a bunch of soil pits and looked to the depth to ice. And what they found was they were probing around with basically an active layer probe, which is a glorified name for a metal stick that you put in the ground to look at how far thaw depth goes. This is not a very technical process, but it's a very useful one. We found the active layer, so that seasonally thawed and frozen layer, was exactly the same as the top of the ice. So this is a system that was in like perfect equilibrium with the climate. So we had our summer thaw, and it stopped at the top of that ice, and then it refroze in the wintertime. And that surface for a tundra area, it is considered like fairly flat at this time. There wasn't really any thermokarst that had formed. And so this whole system was just perfectly imbalanced. Those ice wedges were probably still growing over time. But when I went back after the installation of these in 2016, we found, and this is from a permafrost landscape, a transformation, I'd like to tell you. We were actually really surprised. So this is a picture of Vlad Romanovsky, he's retired now, but he's just a fantastic guy to work with. But he's very Russian, he's very stoic, very calm, like all the time. And I'd worked with him at this point for I don't know, like 7 years or something like that. And I'd never seen him this animated. We got out, and we started hiking across this tundra, and he was just like jumping around and just like so excited that you know, the landscape from his perspective had been completely transformed from this fairly flat landscape into one that was like really heavily affected by thermokarst. And we started hiking around and realizing that, like, you know, we had about a meter of subsidence between 2004 and 2016. And we were like, wow, it's just around this one area. And then we started hiking around and realizing that it was everywhere. And we were flying around between sites, and there was thermokarst features all over the place. And we went up further north to Isaacson. We actually did them in order of Mold Bay, Isaacson, and then Banks Island, which also felt really tropical when we went back down south after Isaacson, which was like being on Mars. But at all of these sites, we saw really widespread thermokarst development. And this had happened, you know, when you think about geomorphological processes, I mean, this is quite a rapid process. And for a periglacial landscape that has been stable for most of the Holocene, so thousands of years, right? And you get these really dramatic changes in a quite a short amount of time. So how had this happened? Well, we had warming, right? But let's look at it in a bit more detail. So when we got back to the lab, we started analyzing our data, and we started looking at climate data from local weather stations. And we looked at the thawing degree day values, and we compared them. We looked at the thawing degree day values between installation and when we returned. And then we compared them to the historical normals. And so that's on the left-hand side. So this plot here, so we've got time on the x-axis and then thawing index or thawing degree days on the y. And so our dotted lines are the historical averages, basically. And then the solid lines are observed thaw index at the sites. And so then we translated this over to a modeled thaw depth, numerically modeled the thaw depth using the Stefan equation. And then we looked at the observed thaw depth in our monitoring stations, and we found, yeah, we have higher than normal thawing degree day values, and then those translate to these anomalously warm summers that cause deeper thaw during that observation period. So remember those ice wedges. So this is the 3 sites: Banks Island, Mold Bay, Isaacson. Those ice wedges were right at the bottom of the active layer, all 3 sites. And so what this facilitated was ongoing subsidence during those summers where we did have anomalously warm weather and high thawing degree days, where we could have subsidence taking place. And what was interesting is that the anomalously warm summers, it wasn't constant. It wasn't like a change in the summer temperature up there. It was kind of some summers were incredibly warm and some didn't meet that ice front. But so there were periods of this summer thaw, but once you lose that ice, you're not going to regain it at the rate that you need to recover the landscape. So we basically saw these key periods of thaw taking place. This is our 3 sites again, time along the x-axis once again, and then this is the temperature of the soil, and so red is warm, blue is cold, and the black line, you can see it, is the thaw front. And then the red dotted line is our massive ground ice. So you can see that most years that red and black line intersect, but not every year, right? So we do have some years that are average temperature or below average temperature in the summer, and they don't, that warming doesn't hit the ice. But these years, you know, even at Mold Bay, where actually we saw the greatest amount of change, it was only 4 summers that were needed to change that landscape completely. So to explore, we were kind of interested in thinking about how these thaw depths would then change over time, like how quickly the system's going to continue to change in the future. But what we found was quite interesting. So again, we've got this observed thaw depth and modeled thaw depth on the left-hand side. And then we used climate change projections for RCP 8.5 and 4.5 to look at future maximum thaw depths. And what we found was that our model projections showed that we weren't supposed to reach, or the projected climate had our thaw depths far into the future. So we were kind of observing thaw depths that were 40 years sooner than these climate models were predicting. And I think this is primarily because they're these like very short, intense, anomalous warming periods, and climate change projections of air temperature don't constrain that very well. And I think it's gotten better since we published this, but it's still quite a big problem that we have these anomalous but like intense short-lived warming periods that have a really big impact on these very vulnerable systems permafrost-wise. And that's really not well captured within these global climate models. So what was also really interesting is around the same time we were noticing these changes, others were too. So this is Tony Lukowitz and Robert Way. This was published, I think, about the same month that we published our paper. And they're working on Banks Island, so our furthest south site. And they were also, we talked to them over the phone after they published this piece, and they were absolutely astounded too. So they saw a huge uptick in permafrost thaw slumps in Banks Island. And also due to kind of these extreme thawing degree day values. So this is in the same area as our long-term monitoring site, but where we saw ice wedge trough deepening, they were also seeing these thaw slumps and increase. I should have included like the images of some landscape change, but really phenomenal like change in the landscape over a short period of time. And then similarly, Steve Kukill, who's on our paper too, working with Bob Fraser, also saw on Banks Island this rapid propagation of ice wedge trough development. So it's interesting, before this kind of geomorphological like watershed moment happened in this high Arctic setting, we really did think these colder landscapes were more stable. But now we're kind of understanding, and when we see the data on the page, it really makes sense and it's quite obvious. But it's really changed the community's mind about where we need to kind of focus our attention when it comes to rapid geomorphological response to these landscapes. So in conclusion on this case study, we needed this really near surface massive ground ice that was like until the mid or late 2000s, early 2000s was in equilibrium with the climate. So we knew that near surface massive ground ice at the base of the active layer. And then this lack of a protective peat layer. So these short-lived, like intense warming periods can have a really rapid effect on the ground thermal regime. And then this increase in thawing degree days during the summer. And then more recently, I've been working with colleagues to, this is a paper led by Dmitry Streletsky. And as a group of us decided it would be really interesting to kind of like do a synthesis of looking at where thaw is happening across the Pan-Arctic. And so again, we generally see much greater change happening in these colder permafrost landscapes where we have ground ice is much like closer to the base of the active layer than we see in warmer permafrost further south, which we can go take a look at. So in this second case study, our observations of these high Arctic systems, we're like, wow, okay, like these high Arctic systems are responding really quickly. What's happening around interior Alaska? Because we haven't really seen really big changes, but like, what's the ground temperature doing? And we have a lot of boreholes, unsurprisingly, like around university area, like interior Alaska, all the way over to the Seward Peninsula. And so we went back to the lab and we were like, okay, let's like see what's happening at these sites in this like warmer permafrost. And we began to look at, we picked out 60 sites in the discontinuous permafrost zone. And these covered a really wide range of vegetation types, different vegetation cover. So we've got tundra and boreal forest sites, some sites that were really close to the continuous permafrost boundary. And all of those sites, we made sure they were not affected by wildfire or man-made disturbance, so that any changes we were seeing were going to be natural condition changes due to, well, using that term loosely, due to atmospheric warming primarily. And so what we found was also astounding. And it was really interesting, right? Because we saw no changes at the surface, but we were seeing these really significant changes in the subsurface. And so we have a bunch of sites we've been monitoring, some since the early 2000s. This is 3 of the 60 that we looked at. And we started to see, this is a bit depressing, really. This is like a heart rate monitor of permafrost, and you're just like, it's just dead, basically. Okay, over the time we've been looking at it. So you see at the beginning of this record, 2010, what we really like to see, because I really like permafrost and I don't want it to melt, but what we like to see is this freeze up curve. So we've got time on the x-axis, temperature here on the y, and this is really happy. In 2010, 11, it froze down to -6 degrees, -8 degrees at a meter depth. That's really nice. But then by the time we get to 2018, we start to see those same depths were not freezing. And in the case of the site at 67 centimeters, it was even above freezing, like some of the in part of the year, which hadn't happened before. And so we started looking through all of our sites and seeing this pattern again and again. And so what was happening was that we were seeing this really interesting transition in our permafrost system, where we have happy permafrost on the left-hand side of this schematic diagram, where we have winter freeze is nice and deep and summer thaw is less than our winter freeze, right? And so in this situation on the left, we have a seasonally thawed layer, which is the same, which is interchangeable with the term of active layer. And then as things warm up and we have an increase, in this case, of thawing degree days and freezing degree days, we reach a point where potential freeze equals potential thaw. And then we shift into the right-hand side of the diagram. And we have our potential freeze is less than potential thaw. And we start to get talic formation. And our active layer becomes a seasonally frozen layer. And that seasonally frozen layer through time thins, and our talic increases in thickness. This is very simplified. And what we actually see is a little bit more complicated than that. But we saw this at almost half of the sites that we looked at. So 44% of the sites, and so this is a map of Alaska. The blue, light blue is our discontinuous permafrost zone. And each of these circles is a monitoring site. So blue sites are happy, they're still permafrost without a talic. And the orange sites are the ones of interest, where we have new talics forming during our observation period. And so we found that 44% of the sites that we were analyzing had new talics. I mean, I should take out the ones that had no permafrost to start with. But this is a huge number of sites, considering all of these before had been permafrost where no talics were forming at all. So this is, now we have a landscape where we had everything freezing during the wintertime. Now it's like this soggy ice cream sandwich, right? You can have flow of water throughout the whole winter. You can have carbon cycling through the whole winter. There's really big implications for hill slope stability and for nutrient mobilization as well. And so this is kind of a game changer for permafrost. And so unsurprisingly, when we looked at our weather data, we saw that these changes were due to an increase in winter and summer temperatures, an increase in freezing degree day values and thawing degree day values. So basically, the summers were getting warmer, but the winters were getting warmer too. And then we also had a little bit of help from snowpack. And so in the years that we saw these talics initiate, we also saw that we had really early snow and heavy snow. And that snow acts as like a giant down blanket that covers a landscape, and it really reduces the rate of heat flux from the soil into the atmosphere. And so this really, really helps to push things over the edge. And it's a really critical part of what's going to happen as we move forward in the future of these talics. So what does the future hold for talic development? Well, it's okay, I have a simplified version of this horrific graph on the next slide. But what we decided to do was we wanted to use our Geophysical Institute permafrost lab model and combine that with historical climate, our field observations, and then projections to look at when the depth of potential freeze and potential thaw were going to be like intermittently kind of like more or less than one another, and then when we kind of shift into a period of time where we permanently get that the thaw is going to be deeper than the freeze. And we looked at that, so that the dotted line is potential freeze, and then the black line is potential freeze with low snow, and then the red line is potential thaw. And so you can kind of see these interacting. We have a couple of different thresholds. So we have threshold 1 and threshold 2. But to simplify the output of this modeling effort, we basically found, these two really key thresholds. And so we have time along the x-axis here, and then depth of potential freeze and potential thaw on the y-axis. And so we have our red line is summer thaw, and then our two black lines are winter freeze. And so we have our low snow. So those are years where there's more chance of things completely refreezing. And then we have our average snow conditions where it's harder for the ground to refreeze. And so what we found was that we're actually in a period right now between threshold 1, T1, and threshold 2 of intermittent talic formation. So our talic formation is really dependent on these like early snow, heavy snow years. And then we reach this threshold at T2, which is basically the point of no return for permafrost degradation in the discontinuous permafrost zone in 2035. That was in 10 years' time. I started studying permafrost like in 2008. And I remember going to AGU and talking to a colleague, and they were like, I think the changes I'm seeing are due to climate change, but I feel really uncomfortable like saying that at this point. And now we're just like this. I mean, yeah, we haven't seen anything like this happening with with permafrost affected systems. And now it's like basically once we hit 2035, and probably even before that, like we're seeing like this mechanism of permafrost degradation is going to be landscape wide. To date, it's been these small hotspots of thermokarst, right? We get these thaw lakes forming on the landscape. It's very isolated in terms of degradation. This is a landscape wide process that will be affecting the discontinuous permafrost zone and propagating northwards through time. So a major challenge in understanding these talics is just we can't see any changes from at the surface. And why is that, right? And so one of the issues is that in the discontinuous permafrost zone, we have a paleo-thaw layer. And so whereas with our cold sites, we had that active layer and the ice kind of met. But in our warmer sites, we have this paleo-thaw layer developed during the Holocene thermal maximum when there was less vegetation cover. And so there was like quicker heat plugs into the ground. And it never recovered. And also we had a lot of sediment redistribution. So we had a bit of aggradation at the surface. And so these ice bodies are actually buried 2 to 4 meters below the base of the active layer. So it's kind of like this lag effect, which means that people are really not paying as much attention as they should be to these talics that are developing. But once we get to this threshold where the talic meets the ice, then we're going to have like the same level of geomorphological change or greater than these high latitude, high Arctic sites as well. So it's a really interesting comparison. We had this cold permafrost that's responding first, and then the warm permafrost is responding later. And so this paper we published basically summarized these findings, these warm summers facilitating this deeper thaw, and these warm winters are preventing deep freeze, and then the snow is helping. And then we have the delayed onset of subsidence due to the paleo-thaw layer. But we're currently in this intermittent phase. And we're seeing it actually after we published this paper, everything in Alaska cooled down and loads of these talics refroze, which was really interesting too. And so we started looking into, looking at projections of, okay, so once we hit that threshold of threshold 2 where talics are not intermittent anymore, how long is it going to take for that thaw front to intersect with massive ice? And when are we going to start to see geomorphological changes in these discontinuous permafrost zones? And what kind of magnitude of change are we going to see when? And so my colleague Dmitry Nikolsky worked with the GIPL model again to look at, out to 2100 potential subsidence. And what we found was that by 2100, for this region, interior Alaska, discontinuous permafrost, and likely a large portion of the boreal forest zone, we'll see between 6 and 7 meters of subsidence if we take into account this ice poor region between 2 and 4 meters, which is not insignificant. And if we take a look at how that's going to impact infrastructure, we developed this ground ice map model for the borough of Fairbanks. So it's about 100,000 people live here, but it's actually a really important hub for oil industry. The Trans-Alaska Pipeline goes through here. There's a lot of the mining industries in Alaska work out of Fairbanks too. And what we found was that around 20% of all buildings and nearly 30% of the road system and large chunks of the Trans-Alaska Pipeline were underlaid by really ice-rich ground that are going to see. So that much of the town is going to be affected by probably 6 to 7 meters of subsidence by 2100. And then up to 70%, probably like on average 60 to 70% of the infrastructure in the whole borough is going to be affected by moderate subsidence, so on the order of 2 to 3 meters of subsidence, which I don't even know. Like, I sit around with my friends sometimes and I'm just like, what is this town? Like, what is this place going to look like? Are we going to have to like boat around like to get to like different buildings? And because a lot of these sites, like a lot of the valleys are really ice rich floodplains. And yeah, I think I have to like invest heavily in gravel so that we can build up the roads. I'm not sure, but it was a real eye-opening study. And the other question that we had was, okay, so this is a discontinuous permafrost zone. And when is this process going to propagate into the continuous permafrost zone? Because once that starts to happen, that's most of the Arctic that is going to be rapidly impacted by permafrost degradation and carbon mobilization and massive changes in hydrology. And so again, my colleague Dmitry Nikolsky, he used a GIPL numerical model to, he combined it with different ecotypes. So we have a lot of ground temperature monitoring stations across different areas of the North Slope. This is the North Slope of Alaska. And this is just a screenshot of a dynamic model. If you're if you're vaguely interested in this kind of stuff, this permamap.gi.alaska.edu page is really, really interesting. Actually, you can kind of look at different warming scenarios and through the century and look at the effects of having gravel pads versus natural conditions. And it's a really interesting tool to play with. But essentially, what we found was talic development starts to occur up on the North Slope around 2060. And then by the time, this is a snapshot of 2100, we have talics of up to 5 meters thickness in what is currently continuous permafrost with a mean annual ground temperature of like -6. So it's a really significant process. And something that we've been thinking a lot about, and we're starting to develop a new project on this front, is this is a paper by Walter Anthony, 2018 in Nature Communications. And their point was like, whoa, these like fall lakes, these abrupt thermokarst features where we have these thick talics beneath water bodies are just like these super emitters of methane, which is a really potent greenhouse gas. And then they were just like, you know, gradual thaw in subaerial conditions are just like really not big players in this carbon cycling game. But then we were like, okay, but what happens when these talics are not just restricted to underneath lake systems? What happens when these talics are underlying essentially the whole of the permafrost zone? That's a really interesting and important question, right? To constrain how much carbon emissions we're going to see when these talics propagate. So we're starting chipping away at this, and Riley just came up to Fairbanks for a couple of weeks of permafrost coring, where we're installing a bunch of monitoring stations across talics of different ages and taking samples from these talics of different ages. So we have kind of a chrono sequence in this interior Alaska area where human disturbance has created talics that we're using kind of as a space for time approach. So we have some that are 110 years old and some that are just 10 years old. And so we have this 6 different sites of different ages, and we're going to look at how carbon emissions from different age talics are producing different carbon emissions. So we can kind of like project, if the natural landscape responds as we predict, how much carbon will this lead to the emissions of. So funnily, this is actually sponsored by Tito's Vodka, which I just found out is an Austin-based company, which is crazy, and that the guy's an alumni from here. So perfect, perfect. I'm just like, yeah, great fit. But yeah, so we're really excited about this project and looking at a range of talics. So this is kind of like just in development, thanks to Tito's, which is great. The other thing, yeah, Tito's vodka. I've actually never tried it, but so the other thing that's happened in relation to talics, and I'm nearly done, so we have a bit of time for questions, is well, I was hanging out in my office one day, permafrost phone rang, picked it up. National Park Service down in Denali, they're just like, guys, we've got some crazy stuff happening on the park road right now. This was like back in 2020 or something, 2021. They're just like, we have this section of road and it is essentially just like collapsing, and it's collapsing. It was collapsing slowly and they were just loading gravel onto it. And then all of a sudden it did that. It just started collapsing. So the red dotted line here is a road, and it just started moving down slope. So they have this huge ice bonded landslide that just kicked into action. It's been moving really slowly for a long time, probably because the permafrost was cold enough. And then we see this like massive uptick in slope movement. Guess why? We have a borehole in the next valley over, and talic initiation occurred in that borehole 1 year before this landslide went berserk and just started falling off the side of this mountain. And they're seeing this happen at several different places along the park road. And we're looking at these geotechnical reports from when the road is built, and there are sections of that road that are built on like 3, 4, 5 meters of solid ice. So federal highways are currently spending $250 million to build a bridge across this section with a 50-year lifespan. So that's just one section of permafrost degradation in interior Alaska, which is pretty bonkers. So anyway, we started working with the National Park Service and federal highways, and we're just starting this project now where we're looking at a combination of hill slope dynamics in Denali National Park, but also trying to create like a permafrost hazard map for the park road corridor right now. And this is in collaboration with colleagues at the USGS. and the guys at Federal Highways too. And so we're really, really excited about this because we're kind of going to go from this tundra, like low, kind of like more like low-lying setting to mountain permafrost, which kind of behaves quite differently. So I'm really excited to learn about this new system. But so we've got an example of another one of the landslides. This is not the road failure. This is a little bit further from the road, but we have these like rapid catastrophic failures taking place within the permafrost. So it's this intra-permafrost failure. And so we're going to really be looking closely at how we can get failure within a column of frozen sediment there. And so we're installing lots of different sensors, temperature sensors, tilt meters, soil moisture sensors, and also looking forward to doing a lot of remote sensing analysis within the system too. But these talics, the more that we start to look into their impact, it seems like they're really affecting lots of different processes. So I'm going to skip that one for the sake of time, but if anyone wants to know about really cool deformation probes, chat to me afterwards. So in conclusion, how are these Arctic landscapes responding to warming? So we see pretty drastic differences between cold permafrost and warm permafrost. And this is primarily due to this cold environments having ground ice very close to the surface and also lacking this really important heat buffer layer. And then we have these paleothaw units within our warmer permafrost that basically is creating like a lag effect that prevents the landscape from responding as quickly. So permafrost in very cold regions is especially vulnerable because of this near surface ground ice, this lack of a protective layer, and this increasing in thaw days. Winter doesn't matter yet up there because it's too cold. And then in this warm permafrost, we have these novel subaerial talics. So we've gone beyond lake systems now, and we're looking at the whole landscape. This novel talic formation has begun to occur. It's intermittent currently, and in around 2035, it's going to become like a non-intermittent process. And then this talic thickness is projected to be up to 7 meters by the year 2100, which is going to have major implications for the built environment. So we're going to have lots of issues with roads and houses. And then lastly, permafrost, we're seeing permafrost thaw and talic formation is also causing issues with hill slope stability too. So on that note, I'll say thank you so much for listening and staying awake. It's really impressive for a Friday. And yeah, I want to take any questions or comments. I just want to say thanks also to all my collaborators and especially my amazing lab group, FAF, Fans of the Frozen, really stretching with our acronym, but we were like, try our best. Amazing group of people. I wish they were here as well, but yeah, let me know if you have any questions. Thank you. Do we have any student questions?
I'm a student. I was a student. You didn't mention the water. You know, there's a lot of water being liberated from ice. I'm fascinated by the sea level connection. I mean, we talk about Greenland, we talk about mountain glaciers, but this is something I was thinking about and going, if that whole landscape starts to melt, some of it's in lakes and ponds locally, but how much of it's getting into the ocean and how is that exacerbating the effect on coastlines that are already being impacted by the melt?
Good question. I don't know if anybody has actually done an assessment of how is ground ice melt going to contribute to sea level rise?
It's an enormous area, right? With a lot of ice.
It is an enormous area with a lot of ice. Yeah. It's a good question. I mean, yeah, maybe that's the next project. Next project. Yeah, that's great. New project ideas coming through. I don't know. I wonder if it would be, yeah. I mean, just even to do a back of the envelope calculation would be really, really interesting. I mean, one of the issues is we have a very bad idea of ground ice volume, which ties into this earlier issue of like, it's just really hard to call permafrost. And so what the big effort right now within the community is to kind of undergo a big synthesis of the data we have, and then people are just really desperate to try and develop geophysical methods that enable us to kind of, so anyway, here is a geophysical survey who wants to get into permafrost. That is a massive knowledge gap right now. So firstly, understanding how much ground ice there is would be the first component of answering that question.
That's the politically very important question now for the world at large.
Right.
Permafrost, you know, if you don't, not in a permafrost zone, it's something that you frankly don't
Yeah.
think about very much.
Yes.
But everybody everywhere is thinking about sea level rise.
Yeah, yeah.
So in fact, it might be something that actually brings attention to the issue.
There isn't carbon cycling.
In a way that gets you money.
Yes. Yeah. Yeah. Which is right now a problem. Yes. Thank you. Yeah.
Thank you for a really awesome talk. I learned a lot about permafrost, which I didn't know to begin with. But maybe a silly question, but you mentioned it only takes 4 years for this landscape to dramatically change. And so I'm wondering if there's like any sort of like mechanism where maybe things might be like anomalously cold to reverse this process that can possibly change. Like, are there like intermediate maybe mechanisms that can like slow the formation of talics? I don't know.
Yeah, I mean, right, like I was saying, things cooled off quite a bit in Alaska. Like after we published the paper, we were like looking at the data sets, and there was quite a bit of like the summers were cooler and the winters were cooler, and so those talics did refreeze, which is slowing things down. If you have a personal, like say if there's someone in Fairbanks and you want to slow down talics around your house, you could scrape away the snow, but there's no natural mechanism that we foresee that is going to slow it down. I think would be worth some effort to look at rate of, once it gets to the North Slope, like continuous permafrost in the tundra, the rate of peat accumulation could, like, so if we have increased productivity, increased thickness of that protective organic layer, it would definitely be interesting to look at like the energy balance there to see, the rate of peat accumulation versus the rate of warming, and whether that peat accumulation could go towards offsetting like the rate of talic development. But in the discontinuous permafrost zone, there isn't really a mechanism quite like that, like because we do have some areas of thick peat, but a lot of the areas where talics are forming are not characterized by peat cover. So that's a really good question. Yeah.
Thank you.
Hello, thank you as well for the talk. I was curious, particularly with the tundra sites that you have pictures for, if you've noticed any change in the vegetation in those environments over time, and whether or not you foresee with any sort of ecological change, there might be a resistance to thermokarst through, I don't know, more advanced
Yeah,
vegetative life.
yeah. I mean, this ties in really nicely actually with the last question. So at the sites that we're seeing this new thermokarst development forming, we see a really drastic change in vegetation, even if the hydrology hasn't changed significantly. So it was quite incredible. At the Banks Island site, just in the troughs, it was like a completely different. It was the same plant community, but the distribution of plants within those troughs was really different. And then not associated with these two efforts, but there's some research that's going on by another group at UAF who are looking at the North Slope of Alaska, which is kind of in between the two sites I discussed. It's like the middle piece, and it is responding differently, which is that there's stabilization through aquatic vegetation growth within these. So these troughs form, and then the ponds form within the troughs, and then plants colonize the troughs, and then to the point where you basically have the formation of a really thick new peat layer, kind of linking into your question. And then that peat layer brings the ground surface up and allows the trough to stabilize. And so a really interesting question right now, again, is to do with this kind of peat accumulation or aquatic plant accumulation within these troughs, and whether, like, how much warming do we need to then reactivate degradation of that ice wedge? Or is that process going to kind of be kind of trying to balance itself out for the rest of the century, or are we going to see a threshold crossed with degradation sooner? But it's something that hasn't been addressed yet, which is really interesting. So there's definitely big changes in vegetation, and the vegetation is really important to permafrost. Yeah.
I'll just ask another follow-up in that direction. For the Arctic sites, you had a very flat landscape, and so presumably the interaction with the air was simple.
Yes.
And now you've got topography.
Yes.
Is there some additional negative or positive feedbacks that are related to that boundary condition changing?
There is, yeah. And so you mean the micro topographic change? Yes, and primarily because of snow distribution, actually. Yeah. And so the formation of these troughs, it really modifies how snow accumulates on the landscape, and when like snow is accumulating earlier and melting earlier or later. But for the most part, you'll see that the snow accumulates more in the troughs, and so it's kind of a positive feedback mechanism that creates a warmer situation within those troughs. And there's a really nice paper by the guy who was working on that high Arctic site with us, Bill Cable, where he did a very high resolution like monitoring study on ice wedges up in UTIG, and he has kind of time series analysis of looking at the heat flux in a. If you're interested, I can share. He's got some really nice time lapse videos of the heat flux and snowpack change in the troughs through time, and it's really cool, like eye-opening to like the ground thermal dynamics of those at that micro topographic scale. Yeah. Two questions.
So my first one is, so you found the correlation between snowpack and tectonic initiation. How about summer or fall rainfall? What are their impact?
That's a great question. These are all really good questions. So summer rain. Initially, there were some observations where people were like, whoa, we're getting advective heat transfer into the soil through rain, warmer precipitation. But there was like a, one of those like paper comment wars. And essentially, they misinterpreted their data, and that wasn't happening. But what we do see is that changes in precipitation patterns are causing a change to the thermal properties of the active layer during the summertime. And I haven't looked too much into that, but rain is definitely, like, if you're looking at modeling at a high resolution, the ground thermal dynamics is definitely something you want to kind of take into consideration. And our group, so Vlad Romanovsky, who was on the first study, or both studies, he's actually been running a long-term experiment at the Smith Lake site on our campus. I haven't checked in with him about what the data looks like, but if you're interested in that, I could connect the two of you, and you can see what that experiment. They have a rain gauge station next to a very high resolution thermistor array to look at the impact of the rain as well. So yeah.
My second question is, you showed your predicted salt front is shallower than the observation, and what do you think are the reasons?
I think it's because the projections, the climate change projection, the ensemble we were using, I think it basically averaged out these extreme weather events, and so you have to be really careful about how you choose your projections and whether you look at ensemble data sets versus not. So I think what we were using basically just did not quantify these anomalous warm events very well. And I haven't dived into literature to look at how much more accurate that's gotten, but I think since 2000, I was writing that paper in 2018, I think probably improved quite significantly though. So it'd be really interesting to go back and rerun those data sets and see if the models now have a more accurate match with what we observed actually. Yeah.
Thank you.
I think we have time for one more question.
You mentioned that there was a permafrost thaw during the Holocene thermal maximum. That sounded like it might have been kind of widespread, but that's also a time when we don't see any change in the carbon dioxide in the atmosphere or methane in ice core records. So I wonder if that tells you something about the Holocene thermal maximum. Does that tell you something about the future? How do you interpret that sort of widespread paleo thaw event in terms of its implications for what's going on today?
Yeah. It's a good question. Yeah, it's funny. So actually carbon, it's on the periphery of my wheelhouse, but I'm giving a talk to Peter's class later that looks at permafrost carbon dynamics more closely. And it got me looking at some of the permafrost carbon emission, Holocene thermal maximum, just after the Holocene thermal maximum, the trajectory of publications from this oh my goodness, permafrost soil lakes, these mega emitters of methane. And then during the course of the last 15 years, the story, the most recent paper is Fairbanks lakes during the Holocene, significant sink but negligible source. So I think it's a really complicated story. I think generally permafrost was not a big contributor to atmospheric methane concentrations during that transition time compared to other sources. So it's fairly negligible. And how that looks, going forward, we're entering a non-analog state, so there could be some surprises. But I think it's probably a little bit too out of my wheelhouse to kind of say anything conclusive. But it was just interesting to look at the literature and to see this kind of arc where we've kind of have a bit of whiplash when it comes to what the main story is there. And then like you're just working, you know, like Ray, you've been working on the story with like samples from Talix around Fairbanks, and it's just so incredibly complicated with like the different feedback mechanisms and involved at every different scale, temporally and spatially. Combined with this, again, revisiting this problem of just like not being able to quantify what's in the subsurface. And there's a lot of permafrost that obviously didn't thaw during the Holocene thermal maximum. And so if we're going to get warmer than the Holocene thermal maximum, right? So then we're going to like enter a stage where we could be mobilizing a significantly larger carbon pool. So I think it's a good question, but I do think that there were some overeager papers around 2008, but yeah. So anyway, it's on to infrastructure now. This is definitely going to be a problem. And then the ground ice quantification, sea level rise, I like that one. Yeah.
All right, with that, before you clap, I just want to make one comment. You may wonder how somebody who does ocean drilling and pore pressure ended up being involved in Alaska, but this is kind of a classic example of what the Blue Sky program at UTIG makes possible. Tanner wrote a proposal to do that, and a big reason why we could do that was through UTIG. So it's really kind of opened up new frontiers for us, and I wanted you to know that. So let's all thank our speaker.
Thank you guys. Yeah. Thanks for thanks for such great questions. And thanks for coming. Yeah.